Welcome again. Now it's time for part 2. So we're looking at the final sample that was posted. This time for part 2 of the final. That means it's topics 5, 6, and 7. So some of the things we have to pay attention to when we deal with mirrors, curved mirrors, and lenses is whether they're convex or concave, because that tells us things about the focal point. Here it says that the focal point is 15 centimeters from the mirror. This means that the focal length is either negative 15 centimeters or positive 15 centimeters. It does not tell you which one is which. Well, a convex mirror is a mirror that bulges outwards. So when we're looking at rays coming in like this, they're going to spread out and go away from the mirror, from each other. It's a diverging object. That means it has a focal point behind the mirror. Focal point is here somewhere, and this distance is then negative 15. So the correct part here is negative 15. Then it says we are going to find a virtual image. Okay, so that means that DI is going to come out as a negative, and that HI is going to come out as positive if we were looking at this. Now, we're not actually looking at the height of it here, but we are told that the virtual image is 10 centimeters along the principal axis from the mirror, but because it's virtual, it's going to be negative 10. So DI is negative 10. Now I can use the equation I call if I do, I die. 1 over F is 1 over DO plus 1 over DI. And when I put in the information we already have, I'm going to put in the 15 for the negative 15 for F and negative 10 for DI. And I should be able to solve this for DO. That gives me a DO that is 30. So now we have found that DO is 30. And then I can go find the magnification. Magnification can be written many different ways, but one of them is negative DI over DO. So in this case, I get to put a negative 10, negative 10, that's positive 10, over 30, I get 1/3, and that's how we get the answer. So pay attention to virtual, real, convex, concave, whether it's a mirror or lens, it all makes a difference. And the signs are important. All right, so what makes a lens work? In this case, we have some light up here that's going through an object, kind of like a slide of some kind, and then it shines into this lens. And what does a lens do? So in this case, we have a lens that's this way. A lens will take light. For instance, if light is coming like this, as it goes in and comes out, it's going to change direction. Light over here, it's going to change direction, change direction. Why? That's because of refraction. So a lens works because of refraction, whereas a mirror works because of reflection. All right, let's see, what are we told here? We have a convex lens. That's a converging object. That means it has a positive focal length. But it even tells you that. It tells you the focal length is 16 centimeters. We want a magnification of 2. So that's an M of 2. I want something twice as big. But is it positive or negative? Well, since I want it on this screen, that means I want a real image. And real images are inverted. And if you look at it carefully, you can see that the happy face got inverted. And inverted have negative magnification. Take a look. Magnification is HI or HO. So if it's inverted, HI is negative. And that means M is negative. So that's negative for real images which are also inverted. Okay, so now I know that my M is negative 2. It's not, the absolute value is 2, but I actually know what m is. It's -2. Let's continue on with this problem. We have more to do. So I'm going to leave a space here. So since m is -2, but it's also negative di over do, that tells me that di is equal to 2 times do. Then I can use my length equation that says 1 over f equal to 1 over do. But instead of di, I'm going to put in that I just learned it's 2 do. I can do a common denominator. Put a 2 here and a 2 here. Now I have a common denominator. And this now tells me that 1 over f, that's 1 over 16, right? F was 16, is equal to, and the right side of the equation gives me f3 over 2 do. And we can cross multiply that and we get do to be 24. Right, you can multiply the 16 here and multiply the 2 do there. And then I have 2 do equal to 48. So do is equal to 24. Continuing on with this, what happens if he puts a convex lens in? That is, he puts a lens in that's like this, thinner in the middle. Well, convex lenses always form virtual reduced images, which means the image isn't going to show up here anymore. You'd actually have to put your eyeball down here and look up this way. And what you'd see, instead of the object, you'd see a smaller, upright virtual image instead of the object. Okay? But a convex lens always forms that. No. I said all that wrong. Oops. Sorry about that. It doesn't say, he says replaces with a concave, and that's my concave lens. And a concave lens always forms a virtual reduced image. A concave lens. A convex mirror always forms a virtual reduced image too, but a concave lens. Sorry about that. All right, so we have a lens in a movie projector. It forms a greatly magnified image on that large screen. So what's true? Well, if we look at magnification, it's it's HI or HO. Let's fix that. There's also negative DI over DO. So if I want M to be really big, I need DI to be a lot bigger than DO. And that's what E says. Because it's on a screen, it would be real. And it is inverted, that's true, but it's real. The image distance got to be bigger than the object distance, so that's out. It's real, that's true, but it's not upright, it's inverted. The image is not located at the focal point, it's located a lot further away. All right, real inverted images. All right, so this might be something you can look at the drawings that we made, that if I have a concave mirror, so focal point may be here, I can put an object here and start drawing in parallel out through F, or I can draw in through F and out parallel, and I found that it formed a real image. So a concave mirror definitely can form a real image. If I have a convex mirror and I try to draw from an object here, focal point back here, in parallel, out as it came from F, in as it's going to F, back parallel, they're not meeting, but they look like they met back here. That's a virtual image. No matter what you do with that convex mirror, you'll get a virtual image. What about a plane mirror? This would be where you're standing in front of the mirror, or maybe it's a triangle or something, and you start figuring out where the image is. It's always behind the mirror. That means it's always virtual. So to get a real image, only the concave works. All right, polarization. When it starts unpolarized, this means that the first filter is always takes half of the light out. So what does it say here? It says the first point is horizontal. So I have some unpolarized light here. By now, it's polarized this way. So whatever intensity I have here, I now have half. That intensity goes into the next one, and the next one says it's rotated at 68 degrees. So now I have light rotated in that direction. The intensity that I get at the end will be the intensity going into that last filter times cosine square of the angle that it was before the last filter, that's horizontal, and the angle is afterwards. Well, that's 68 degrees away from horizontal. So this is the calculation we need to do. And that comes out to 0.070, which you can multiply it by 100 and change to 7%. And that's how we get that answer. So make sure you pay attention to, if it starts out unpolarized, your first part does half. And then make sure you pay attention to if the angle given is the angle between before and after. It was in this case, but that's not always going to be the case. All right, so this is the idea of shining light through, and the diffraction grating is a series of openings. Light comes in and will go straight through, but there'll also be some that will give you a constructive interference up here at a first order, and up here at a second order, and likewise down here. So that's the drawings that we know from Young's experiment. But this is asking what phenomena happens at the first order bright spot. Well, what happens is that light from different openings in the diffraction grating are going to meet up and have constructive interference. The light from, if I have two openings, the light from the top opening and the light from the bottom opening travels one extra wavelength from the bottom opening than the top opening. So they start out in sync, one travels one extra wavelength, and they're back in sync again at the first order. Constructive interference. In between the bright spots, you have destructive interference. You'll have darkness. Then it says the scientist changes from a red laser to a green laser. This means that we're going for a shorter wavelength. You should know that, but the problem also says it. What happens to the distance to the first order? It should have said X with a subscript, but okay. This is one of the places where you can use the approximation that's on your equation sheet. That approximation specifically says that X1 would be about equal to 1 times lambda times L divided by D. So if I'm going to a smaller wavelength, lambda, I'm going to get a smaller X. If you were to calculate it, the approximation is always dangerous because it's not going to give you exact answers, but it is helpful to just tell these kind of things, like if I change this, what would happen to that? Now we're going to go calculate something. So on the equation sheet, it gives me an equation that says that D is sine theta m, E times sine theta n is equal to m times lambda. Well, it says here that we're doing the second order. That means m is equal to 2. But it also says that we have 500 lines per millimeters. This means D is equal to 1 millimeter divided by 500. So if I want to find the angle here, I'm going to put in that information. So I have 1 millimeter. That's 1 times 10 to the negative 3 meters divided by 500 is equal to, and then we get, no, I'm sorry, not equal to, that's sine theta 2, and that's equal to 2 times, and then we have the wavelength here, 680 times 10 to the negative 9 meters. My 9 looked a little bad here. By the time we're all finished with this, maybe I'll get good at writing this. All right, so this becomes a question of rearranging. You multiply by 500, you divide by 1 times 10 to the negative 3, and then you take the inverse sign, and that's how you get the answer. If you did not realize this at second order, and you had put a 1 in here, you would have gotten C as the answer instead. All right, now we're heading into topic 6, starting here with the photoelectric effect. That's when a photon comes in and kicks a photoelectron out. The equation that determines some of this goes like this. The maximum energy of that electron is the energy of the photon coming in minus the work function. So on the equation sheet, you'll see it like that. So here I'm seeing that if I make the light brighter, change the intensity, nothing happens to the kinetic energy. Well, this equation is giving us a little bit of a clue that it has nothing to do with intensity. So what is it that happens? Well, every single photon coming in has this energy and has the ability to give an electron this energy. Shining more photons in is not going to give the electrons more energy, but it's going to make more electrons come off. So it's going to increase the number of photoelectrons, but not the energy, since the energy does not relate to that at all. So A is a good answer. It says that each photon has the same energy to be able to transfer to photoelectrons, but regardless of the intensity. There's just going to be more of them. So what about this? We are supposed to decide, what does the maximum kinetic energy depend on? Well, the equation tells us, but we have to look a little bit beyond the equation itself. So it does tell us it depends on frequency. That wasn't one of the choices here, but keep in mind that frequency and wavelength are related. So that means it depends on wavelength. And since wavelength and color have to do with each other, it depends on the color. And I also see here that it depends on that work function. But it does not depend on intensity, which is exactly what this equation says. It does not depend on intensity. And it has nothing to do with the size of the metal, so it doesn't depend on that. So we get to say that it depends on 1, 4, and 5. So we have to pick that answer. All right. Now we're going to change from using blue light to using violet light. And then he finds out nothing happens. Why? Well, if I plot the equation we've written a few times, kinetic energy through the maximum kinetic energy is equal to HF minus work function. If I plot that, it looks like this. And if your frequency gets too low down here in this range, if your frequency is here, you won't get any. Because this means H times F minus lambda is negative, minus work function is negative. And you can't have negative kinetic energy. So when you change from blue to yellow, you make for a smaller frequency. And apparently he got so low that he got below that frequency here that's called the threshold frequency. He got below that. So now he's no longer able to get anything, any electron to come off the surface. All right. What about this? I want the largest wavelength that could result in production from the surface with this work function. So this is the equation again. So I need a positive. So I'm going to just find out which wavelength will give me 0. And then I know any wavelengths that are smaller than that will not work. No, that will work, but any wavelengths that are larger than that will not work. Why is that? That's because if I replace frequency with wavelength, frequency is equal to speed of light divided by wavelength. If I'm putting in the 0, I'm now finding the maximum wavelength. So if you rearrange this, I get to add the work function and do some cross multiplication. So I end up with lambda max times the work function equal to hc divided by the work function. So I have the wavelength if I solve this. Well, since I have the work function in EV, I'm going to use Planck's constant in EV. That's 4.14 10 to the negative 15 EV times seconds. And then I get to multiply that by 3 10 to the 8 meters per second. And once I'm finished working that out, I will find that this gives me, well, let's see what it gives me. Put it on the calculator and actually do it. 4.14 e negative 15 times 3e8 divided by 2.1. That gives me a wavelength that's 5.91 10 to the negative 7 meters. That would be 591 nanometers. So I cannot go any higher than that, but I can go all the way up to that. So of these ones given, these ones would not work. These three would all work, but which one is the biggest of the three that will work? That's the 570. The tricky part of this problem is that you're not actually calculating one of the answers, but you're picking the answer based on that calculation. All right, now for some atomic physics. So Paschen series means we are landing in n equal to 3. So Bohr's equation for transitions in the hydrogen says, or for any transition really, says that HF is equal to EI minus EF. So I want the wavelength, so I'm going to replace frequency with wavelength, hc divided by wavelength. I'm going to come from some initial state, and I'm going to go to 3. That's what it says, that we're going to end in 3. But what is my initial state? Well, I want the shortest wavelength. So this means I want my left side to be the biggest possible. This means that I need my right side to be the biggest possible. So this means that I will be coming from the highest energy level possible. That's the infinity level. And I'll land in 3. And there's HC, and this is then the shortest wavelength. So you might put it as a little minimum here if you want. But I need to calculate those two energies. So E infinity is, well, it says here how to calculate it. Minus 13.6 divided by an infinite number squared. I know you can't really do that, but that comes out to 0. Okay, E3, negative 13.6 EV divided by 3 squared. Get the handy dandy calculator, and I get 1.51 EV. There's still a minus in front. So now I have HC over lambda is equal to 0 minus negative 1.51. Now you're going to solve this for the wavelength. So it comes out similar to the previous problem of solving. So let's erase something here and work this out real quick. So I can multiply by wavelength and divide by 1.51. So I get that the wavelength is HC divided by 1.51 EV. This means I would put in Planck's constant in EV. and then speed of light. Meters per second. Not very successful in getting that to all show there. Divide by 1.51. That's going to give me 8.2 times 10 to the negative 9 meters, which I can change to nanometers, and that's what was done here. It was not negative 9, it's negative 7, which I can change to negative 9 and get nano. Now that's a little bit longer wavelength than what the red light has. That's infrared. All right, wave behavior of particles. Well, keys for wave behavior is things like diffraction or interference. Those are our kind of key experiments. If I can get a particle to create an interference pattern or to do diffraction, bending around corners in some way, I have shown a wave behavior of that particle. And that's what was done in the electron diffraction experiment. The people who did that, the two scientists, were Davison and Germer. So you might have seen it as Davison and Germer's electron diffraction experiments. All right, so here's the passage that goes for problems 17 through 19. If I look at X-rays, X-rays are produced when you shoot electrons on a target with a high energy, and then photons come off, and if the energy is high enough, instead of being visible or ultraviolet, it gets up in the X-ray range. Well, the spectrum, when we analyze the X-rays we get, the intensity has a minimum wavelength. But below that, you won't see anything. And then it comes and goes and kind of follows this nice curve with a couple of peaks on it. Okay. So let's see what the question says. What does that minimum cutoff wavelength correspond to? Well, if I have a minimum wavelength, this corresponds to having a maximum frequency, because frequency is c divided by wavelength. That was not maximum, that was minimum. Maximum frequency corresponds to minimum wavelength. What did I just do? Here we go. All right, well, that corresponds to a maximum energy, because the energy of a photon is Planck's constant times frequency. So that's the answer here. It corresponds to the highest energy of the photons emitted. But we might ask ourselves, why is there even a cutoff? Well, that's because those photons cannot have any more energy than the energy of the electrons coming in. And they came in with some electric potential energy turned to kinetic energy. They came in with their charge times the voltage used to accelerate. Okay? This is the energy we are putting in, shooting the electron on. This is what we get out in the form of photons. You can't get more out than you put in. Now, you can get photons out with less energy. That would be a higher wavelength. That's the rest of the spectrum. That's because some of the electrons that are shot in will lose energy in more than one step. All right, so we looked at the spectrum and we saw these peaks, where this is K beta and this is K alpha. Well, since the K alpha has a higher wavelength than the K beta, this means that the alpha peak has a smaller frequency. And since Planck's constant times frequency is the energy, the K alpha must have less energy. So K beta has the higher energy, but there are two choices for that, for these two. So now we need to look at which one is more likely. Well, what happens is that electrons come in and they shoot out of n equal to 1. they shoot an electron out of there. And that means electrons from n equal to 2 might fall in here, or from n equal to 3. K alpha is from n equal to 2 into n equal to 1. K beta is from 3. So this is the alpha and this is the beta. So it's not a surprise that we can have more electrons coming from 2 to 1 because it's closer. But how does that show up on the graph? Well, it shows up as having a higher intensity. So of all these times where an electron gets knocked out from the lowest energy level, many more times of those times we get an alpha than we get a beta. That's why this gets to have a higher intensity. If you looked at it, maybe you say the area of the alpha is about 4 times the area of the beta. This means that for every 1 beta transition, we'll get 4 alpha transitions. Okay, the last question on that says that we are increasing the current in a filament. This means that I'm going to have more electrons coming, hitting the target and creating the X-rays. All right, but the voltage is kept the same. This means that the energy, the electrons will come with the same energy because the energy of the electrons were given by the voltage. So what does this create? It creates an overall higher intensity. More electrons in means more photons out. But since I'm not changing the voltage, it does not change the minimum wavelength. So it will remain the same. You have to change the voltage to get more energy in or less energy in, which would then change the minimum wavelength or maximum frequency for the photons, the X-ray photons. When the nucleus emits an alpha particle, what's true? Well, let's say I have some nucleus here that decays into something else. And then there's an alpha particle. But what's an alpha particle? An alpha particle is really a helium-4 nucleus. So if I have a number here, that would be atomic number. Then the atomic number right there would be 2 less. See, 2 minus 2, it would be 2 less. If I'm looking at the mass number up here, the mass number here would be 4 less because it has to match these. So the atomic number decreases by 2, the mass number decreases by 4, the neutron number decreases by 2 because the helium has 2 neutrons. So these are the different choices we could be picking on there. You should know the same answer if I dealt with a beta minus decay or beta plus decay. All right, so we have sodium-24 with a half-life of 15 hours. How many hours will go before we get 4% of the original? So we might go something like this. We'll say after 15 hours, I would have 50%. After 30 hours, 2 half-lives, I would have 25%. After another half-life, that's 45, I would have 12.5%. After another half-life, that would be 60. I would have 6.25. I'm just dividing by 2 every time. After another half-life, that would be 75 hours. I would have half of that. That would be 3.125. I could just sit to my calculator and divide by 2. Well, my 4% happens to happen between here. So it's more than 60 hours and less than 75 hours. So this looks like a good answer. In fact, it's the only possible answer there. So that would be a fine way to do that problem. But you could also go and actually solve it. So you could say that I have an R equal to the initial weight E negative lambda T. I want my R to be 4% of the initial weight. So I can cancel out that initial weight. And then my E, what do I have? I have lambda, that's the natural log of 2 divided by half-life, and then times T. if I put the half-life in hours, and then I rearrange and solve this for t, my t will come out in hours. It will match whatever I start with. So the first thing to do is take the natural log of 0.04 on the left side, and on the right side it now says minus natural log of 2 divided by 15 hours times t. So you can multiply the 15 hours, or you can divide by the natural log of 2, and the minus is going to cancel because the left side is negative. And that is how you can solve for t. Make sure you can do those solutions. This happens to be one that could work this way, and that's not unusual for multiple choice, but don't count on it. What if there had been 2 answers that were in that range of being in between 60 and 75? All right, we have a beta, no, we have either alpha or beta decays here, but we have lead to 12. And we could try to see, so we're just going to try. Let's try if it's an alpha decay, the first decay. But it says that lead is decaying, and then it's going to land on either this one or this one, and then it's going to decay again and end up on this one after 3 decays. Okay, so lead 212, if it's an alpha decay, then I'm going to have an alpha particle here, that's helium-4, and this means this would be 80, and this would be 208. Well, I don't see that as one of my choices. I don't need a periodic table to look this up, but I should go look up what 80 is just for the fun of it. That's mercury. But this is not it. So the ones that starts with an alpha decay are all wrong. So now I'm going to go and say, okay, so we need to start with a beta decay. 212, lead, and then it's a beta decay. And if it doesn't say anything, assume it's a beta minus decay. You can try a beta plus and it won't work. It won't match one of the ones you have. So what's a beta minus decay? That's an electron. This means the charge is -1 and the mass is virtually 0 compared to the nucleons. So this means I'll have 212 and then I'll have gone to 83. Oh, look at that. That's one of the answer choices. That's bismuth. So the beta decay was good. But now we need to say, what is that going to do? Because I see the choice here that after the beta, I either have alpha or I have another beta. Okay, so if you try the alpha, you'll find out it doesn't work. I'm just trying the beta again to show you that it does work. So if I try the beta again, I get another electron coming off. This means that this goes to 84. And look at that, that's the polonium. And then you can try the last one, and that's taking the polonium. I'm going to do it all the way at the top here. I can take the polonium, 84, and have it decay to my final product, 208 lead. What kind of decay would that be? Well, since I have 4 less on the mass number, I need a 4 here and I need a 2 here. And that's an alpha decay. So it does do a beta-beta alpha. You should be able to do similar problems with different elements, different isotopes, and still figure out the sequence. Excuse me. The activity rate, that's R. We're trying to find R. So it says that on the equation sheet that R is equal to lambda times N. But I know what lambda is because I'm given the half-life. So lambda is the natural log of 2 divided by half-life. So I can figure that out, but I also need to figure out N. So let's go figure out N. If I have 0.024 grams, I can use a little conversion from chemistry and say that every mole I have, how many grams? Well, it's cobalt 60, so it's going to be really close to 60. The molar mass of any isotope is the mass number in grams per mole, close enough. So then I can use Avogadro's constant to get from mole to nuclei. That's 602, 10 to the 23. And that allows me to calculate n. So let's take a moment and do that. 0.024 divided by 60 times 6.02, 23. That gives me 2.41 times 10 to the 20th. So that's going to go as n up here. 2.41, 10 to the 20th. What's going to go for half-life? Well, it says that we have 5.27 years, but I need that changed to seconds. Didn't give myself a lot of space for this. 5.27, that's years. Then we multiply by 365. Then we multiply by 24 to get hours, and by 60 to get minutes, and by 60 to get seconds. So that whole part goes in there. So we take the answer from before and we multiply it by the natural log of 2. And then we start dividing by this whole parentheses of 5.27 and 365 and 24 and 60 and 60. And that gives me 1.004 times 10 to the 12. That's how we get that answer. You should be able to do this, to find n if you know a mass, and to use and to find lambda knowing a half-life. That's on the equation sheet. But finding n using a mass is a piece of unit conversion, essentially, from grams to moles to nuclei, that you should know and have seen many times. All right, ratio of neutrons to protons for naturally occurring isotopes. So this is the one that could be graphed like this, that if I put atomic number, a number of protons here, and a number of neutrons here, and I look at the line where n is equal to z, then I'll get that all the naturally occurring stable ones are going to be very close here. And then they start going up this way. All the naturally occurring isotopes. So that happens somewhere around 20. So for small atomic numbers, you have the same number of protons as neutrons. Examples: carbon 12, 6 of each. Nitrogen 14, 7 of each. Oxygen 16, 8 of each. It's very typical for the low elements to have that. But for the higher elements, to take an example and go really high, uranium. Uranium is 92, and we have 235 or 238. Typical 238 is the most common isotope of it. Well, if it has 238 neutrons and protons combined, but only 92 neutrons, this means it has 146. 92 protons and 146 neutrons, a lot more neutrons than protons. That happens when you start getting past atomic number of 20. All right, so to balance this reaction, we really just have to identify what the alpha particle is. And then I look at the top here and I have 18. So this means that over here on my question mark, I need a 1 because I already have 17 going. On the bottom here, I have 9. Well, on the bottom over here, I have 8 already, so that means I have 1. So I need something with a charge of 1 and a mass of 1. That would be a proton. This is not a naturally occurring radioactive decay, but rather it's a nuclear reaction where an alpha particle is shot onto a nitrogen nucleus, not a nitrogen isotope. All right, an alpha decay, what would I get? Well, you might say I need a periodic table to know what it's called, but you really don't. If I wrote radon, radon is Rn, and 220, and then I do an alpha decay, I know that what I'm going to get here is going to be 216. I don't actually need to know anything else because there's only one of them that has 216 here, so that makes that the right answer. But if I did go and look in the periodic table, I'll find that radon is 86, and this would end up at 84, and then I can find on the periodic table that 84 is polonium. This is one of the ones that Madame Curie and Pierre Curie worked with back in the days. All right, finding the energy, whether it's a binding energy, looking at neutrons and protons, putting them together to form an isotope, or it's the energy of released in a nuclear reaction or decay. Either way, it's about finding the change in mass. Let's write this reaction. So this is radon 222, just a slightly different one than one we looked at before. And it's decaying in an alpha decay. So we said before this was 86. Not important in this problem, but it decays to polonium 218. So I have a mass before, and I have a mass afterwards. I'm going to see how much mass I lost. So this means I'm going to take the mass of the radon, and I'm going to subtract the mass of the polonium and the mass of the alpha particle. And I'll see how much mass is lost. So this becomes a question of taking the numbers. They're right here. You take this number, and this number, and you just subtract them and see what you get. So let's try that. 222.01757. Be careful, don't round too much here because it's going to be the decimals that actually matters in the end. So we subtract from that 218.008973 and the 4.002603. This comes out to 0.005994. That's atomic mass units. I need to calculate the energy. Sometimes we see it as E equal mc squared. That's the conversion from mass to energy. It happens to be called a Q value when you're calculating the energy released in a reaction. So I'm going to call it Q, but that's not really important in this problem. So I have this mass it's really a change in mass that gets multiplied by C squared. So 0.005994 U has to get multiplied by C squared, but here's the trick. On the equation sheet, there is a factor that says that 1 U is 931.5 MeV per C squared. Well, this allows me to cancel out the C squared and the U, and then just do this multiplication, and that ends up at 5.58. Last problem. Röntgen equivalent in man. You should be familiar with those parts that we were doing at the end of topic 7 about absorbed dose. That's the amount of energy that's absorbed. And then when you multiply by the RBE, the radiation, the relative biological effectiveness, RBE, then you get the equivalent to what X-rays would do. So once you have multiplied by that, you have a value for the damage caused by any radiation that you can compare because they've all been normalized or normed to X-rays. So it works, it's the potential damage caused by any radiation on a scale that's comparable from one type of radiation to another type. Okay, that concludes my screencast going through all the answers on the second part of the sample practice that was posted. Until next time, stay safe, stay home, stay healthy, and have fun.